Hello everybody. In the last class we concluded our discussion on three-phase circuits. A natural extension to the three-phase circuits would be the three-phase transformers acting as loads on the three-phase sources. Today's session will focus on discussion on three-phase transformers. Recall that we had already studied the single phase transformers. All the principles of the single phase transformers are applicable to the three phase transformers also. In fact, we use three single phase transformers and connect it in either star delta fashion to obtain the three phase action. The Faraday's laws of electromagnetics, that is E is equal to n d phi by dt, the Ampere's law, and all the notions of leakage inductance, the mutual inductance, the core loss, the hysteresis loop, all those concepts that we studied in the single phase transformers are equally applicable to the three phase transformers also. In fact, the equivalent circuit will also be similar. Now, to start the discussion on the three phase transformers, we shall assume that we are having three single phase transformers and we will connect them in a particular configuration. So, let us start with three single phase transformers. So, you have the primary and the secondary, and we will say that is 1:n. We have another single phase transformer with primary and secondary, which is also having 1:n, and one more single phase transformer with primary and secondary with turns ratio 1:n. These are three single phase transformers. Now, it has three primaries. We will call that one as A P, B P, C P. Three primary windings, A P, B P, C P. Let us say the dots are shown to indicate the polarities. And then there are three secondary windings, and we will call that one as AS, BS, and CS with dots indicated as shown. So, we have three primary windings and three secondary windings. Now, the three primary windings can be connected in one of the topologies star or delta, and the three secondary windings can also be connected in one of the topologies, that is star and delta, which will result in four topologies for the entire transformer. Now, all the non-idealities of the practical single phase transformer are also applicable to each of these three single phase transformers. However, for the purpose of discussion, we assume that we know that there are practical non-idealities will exist. However, for the conceptual understanding of the three phase transformer, we shall not include these non-idealities in our discussion now, but keep in the back of the mind that all practical transformers will have the non-idealities like the core loss, will have a finite magnetizing inductance Xm, reactance, that is the magnetizing reactance Xm. It will have a finite leakage reactance on the primary side, a finite leakage reactance on the secondary side, a finite winding resistance R primary, a finite winding resistance on the secondary side R secondary. All those non-idealities which we had incorporated in the equivalent circuit of the single phase transformer is equally applicable to each of these single phase transformers. However, we are just taking the ideal transformer concept and developing the notion of the three phase transformer here. But keep in the back of mind that all these idealities are present. Now, these three single phase transformers can be connected such that on the primary side and on the secondary side we can have the following topologies. So, first we could have on the primary side delta, that is all the three coils AP, BP, CP are connected in a delta fashion, and the secondary AS, BS, CS are also connected in delta topology. And then we can have the primary connected in the delta fashion, delta topology, and the secondary connected as star. And the third, we have the primary connected as star, the secondary connected as delta, and the fourth, we can have the primary in star, the secondary also in star topology, which means we have a circuit in the delta topology and a delta topology on the secondary side, that is called delta delta connection. We have a delta topology on the primary side, a star or a Y topology, we can call this also as a Y topology on the secondary side. So, this is called a delta star connection, and we have a star and a Y topology possibility on the primary side and a delta connection on the secondary side, and that is called a star delta connection. And of course, finally, we have a star connection on the primary side and also a star connection on the secondary side, resulting in a star star connection or a Y Y connection. So, these are the possible connections that one could make with the three single phase transformers, and based on these type of connections the nomenclature of the three phase transformers are made, that is delta delta, delta star star, delta star star type of connections. Now, let us take each of these types, each of these four types, study the various current and the voltage relationships across the phase and the line, and also the phasor diagram for each of these types of topological connections. So, first let us say we make the connection as delta delta, which means that the primary windings AP, BP, CP are connected in delta, and the secondary windings AS, BS, CS are connected also in delta. So, which means that we have the primary which is connected like that, so these are the three primary coils. Now, the secondary coils are also connected in delta, as shown here. Now, there is mutual inductance between the primary and the secondary, and that is shown as coupled, okay, by means of a core. Now, the primary, you have the A, B and the C lines connected to the sources as shown. This is the A, B, C lines. Okay. So, this would be your AP coil, the BP coil and the CP coil. So, the dot polarities are as shown. Give some thought to the dot polarities. We are keeping the direction of the voltages like this. This is EAB, isn't it? EAB, EBC, EBC, and then you have ECA. So, therefore, we are having the following dot polarities and these are the dot polarities as given. Now, for the secondary, we have AS coil, the BS coil and the CS coil. And let us say the dot polarities are in this fashion as shown. So, which means the voltage, this would be E across coil AS, but we will give some point AB prime for the secondary, or let us say this has a prime attached to that one, and this voltage will be EBC prime to indicate it is on the secondary side, and we have ECA prime to indicate that it is on the secondary side. Now, we take out these voltages here on the secondary side. So, you have the A prime, B prime, C prime. These are the secondary terminals which will go to further loads. So, it should be assumed that on the primary side it is connected to the a source, 3-phase source, and on the secondary side it is connected to a well balanced 3-phase load. Now, here we have 3 currents, that is IA primary, IB primary, IC primary, and the 3 currents coming out of this line here, and we will call that one as IA secondary, IB secondary, IC secondary. Now, this is a delta-delta connection. If we say that the load is well balanced, then, and let us say the effective values here is equal to I and I. That is, the line currents on the primary side are I and I. Then the phase currents in each of these phases, that is each of the primaries of the single phase coils, would be I by root 3, I by root 3, I by root 3, isn't it? So, this would be I by root 3, I by root 3, and also I by root 3. So, the phase currents are I by root 3, I by root 3, I by root 3. Now, this transformer is a 1:n transformer ratio. So, the voltages get multiplied by n and the currents get divided by n. So, the phase currents which are flowing here, which are flowing on the secondary. So, if it is entering the dot on the primary, it is leaving the dots on the secondary. So, we will put the direction like that. It is leaving the dots on the secondary. Now, all have value I by root 3 n, I by root 3 n, I by root 3 n. So, these are the phase currents in the secondary, and then what comes into the line of the secondary would be I by n into root 3 times. Root 3 times phase current will be the line currents, I by n and I by n. So, this is how the current mapping occurs as it flows through the 3-phase transformer topology. And the voltages, let us say all the line voltages are equal in the case of the, meaning the effective values of all the line voltage in the case of the delta, and the phase voltages are the same. So, we have EL as the line voltage effective values and which are also the phase voltage effective values. So, what happens here is you have n times EL as the phase and the line voltages which are occurring on the other side, that is the secondary side. So, let us look at the phasor diagram of this. Let me push this up a bit. We shall push this up. Okay. Now, starting on the primary side, we have EAB. This is the EAB axis. So, I will say this is the AB axis, this is the CA axis, and this is the BC axis. All are 120 degrees out of phase with each other. Now, if we take the case of the delta, the line currents will be lagging the line voltages by 30 degrees. If it had been resistive loads, but as they are not resistive loads, they will lag by a further. So, the IAP would be along BC, IBC would be along CA, and CA will be along IAB, the phase currents. Now, let us take the voltages. So, this would be EAB, ECA and EBC on the primary side. Now, if you take the dot polarity, the secondary also will be along the same directions. So, but only by a factor of n it is going to change. So, let us say that we have EAB prime, which is n EL, this is EL if n is less than 1, let us say, and then you have ECA dash, which is again n EL, and you have EBC prime. which is also equal to N E L effective value. So, this would be the relationship that you would have in the case of the delta-delta connection. Now, let us look at the delta star connection. So, let us say we have the delta star connection. So, in the delta star connection, the primary is connected in the fashion of the delta and the secondary is connected in the star or Y topology. And as usual, we have the three primary phases which are now connected in delta like before. We have the primary. So, we have here the A, we have the B phase of the line, and then you have the C. So, these are the 3 points the delta. Let us have our polarities in sequence like that. This would be the AP phase, the BP coil and the CP coil. Now, the secondary is connected in star fashion. So, let us like this. This is the secondary connection, and let us also put the dot polarities all away from the neutral. One end of the secondary windings are connected at the neutral. These are AS winding, the BS winding, the CS winding. Now, this is the neutral point. The voltage across the AP winding is EAB, which is equal to EL. Now, this and AS, the voltage across the coil of the AS has a ratio 1:n. So, the coils have the ratio 1:n. So, when in the delta star connection, when there is a indication of turns ratio, the 3-phase transformer, we say that the primary side phase coil to the secondary side phase coil, or the secondary side phase coil to the primary side phase coil, whichever is applicable, that would be the scaling factor that you have to use for the voltages. So, if it is EL here, then the voltage across just only the S coil, which is the phase circuit coil, would be N times EL. Likewise, we have the EL across BP coil and EL across the CP coil, and therefore, you will have voltages in this fashion here, N times EL, N times EL. And therefore, If you look at the phasor diagram for this, let us take this selection tool. Let us copy and paste. Let us consider the phasor diagram of this. This is the secondary side. This is the secondary side. And this is the primary side. And of course, this would be connected to the three phase load A prime, B prime, C prime. Now, if we take, let us say, the load side, EAS, the BS and CS, they are all the phase voltages of the star circuit. So, let us draw the phase voltages of the secondary side, which is E, let us say A dash N, let us say that is the reference, this is EAS, that is this voltage what I am showing across the AS coil, and E B dash N, this is across the BS coil, and we have E C dash N, which is the voltage across the CS coil, taking E A dash N as the reference line, the horizontal line. They are all 120 degrees phase shifted with respect to each other. Now, the line voltage, that is A dash E A dash B dash, is 30 degrees leading, and I will show that as a different, is 30 degrees leading like that. This is E A dash B dash, which is nothing but E A dash N plus minus E B dash N, which is what we have shown here. And likewise, it is 30 degrees leading for all things E C dash A dash and so on, E B dash C dash. Okay. So, that is 30 degrees leading. Now, if we look at the primary side, there is exact one-to-one phase relationship, the in-phase relationship between the voltage across AP and the voltage across AS, because of the dot polarity. Okay. So, therefore, on the primary side, if you see AP, which is the phase voltage along this, is along A dash N dash AB. So, that depends of course on the ratio. So, E A dash N dash is NEL, isn't it? This is NEL, NEL, NEL. So, along this line itself we will have EAB on the primary side. So, let us say n is less than 1, and therefore, we have EAB, EBC, ECA of the primary circuit. So, if we look at the terminal voltages of this transformer, that is E A B, E B C, E C A, and the terminal voltages of the secondary E A dash B dash, E B dash C dash, and E C dash A dash. There is a 30 degrees phase shift between those two, and of course there is also a matter of amplitude which comes into the picture. This is, the values are EL, EL and EL, amplitude. That is, if we are applying EL as the line voltage on the primary side, if we apply EL as the line voltage on the primary side, this is the EL that becomes converted to N times EL on the secondary phase coils, which becomes root 3 into N times EL on the terminals of the secondary of the transformer. So, what you get here would be root 3 into N EL. So, this is root 3 into N EL, root 3 into N EL, root 3 into N EL. So, that would be the amplitudes of the voltages there. Now, with a phase shift, now you see that the primary 3 terminals and the secondary 3 terminals are phase shifted with respect to each other by 30 degrees, and on top of it the amplitude is root 3 N times. If EL is applied, what you get at the terminals would be root 3 into N. Remember that. And then if there is a current I which flows through the line of the primary side delta, on the face it becomes I by root 3, and this I by root 3 becomes I by N root 3, and on the line it is same as the phase in the case of the star circuit, and therefore the currents here are I by N root 3. That is the relationship. So, remember, in the case of the delta delta, two things that you need to remember always. If you apply a voltage of EL, the voltage on the secondary side, that is secondary side is at the terminals would be N times EL, and if the primary line current is I, then the line current on the secondary terminals is I by N. This is for the delta delta. In the case of star delta, on the primary side, if you are applying a voltage of EL, then on the secondary side what do you get? EL becomes NEL phase voltage into root 3. So, root 3 NEL on the secondary side. Then this is primary, secondary. Then if you have a line current of I on the primary side, this results in I by root 3 in the phase current, the phase coils, I by N root 3 in the secondary phase coils, which becomes the line currents, and therefore you have I by N root 3 in the case of. So, we shall summarize this later. Then we have the third connection, which is the star delta. The star delta connection is exactly similar to this topology, except that the power, instead of being flowing from the delta side to the star side, it is flowing from the star side to the delta side, like the primary and the secondary are reversed. So, we have the primary connected as a star, as shown here. The secondary is connected in delta, as shown here. Let us indicate the polarities. Never forget to indicate the dot polarities in the three phase transformers in sequence. So, let us say this is the A P coil, the B P coil and the C P coil, and this is the A S coil, the B S secondary side coil and the C S coil. The coil on the primary are connected as shown. We have the connections in this manner. So, you have the A phase, B phase, C phase sources connected to the primary. Now, there is induction, turns ratio 1:n between the phase coils of the primary and the secondary, and the secondary is connected to three phase balanced load in this fashion, and we will call that one as A prime, B prime, C prime. So, if we apply a voltage, EL on the primary line to line, the phase voltage across the A phase coil is EL by root 3. Now, there is a turns ratio which comes into the picture between the phase voltage of the A phase coil and of the primary and the secondary, and that is N times EL by root 3. Now, that is also the voltage that comes across the line voltage that comes across the terminals, which is N EL by root 3. So, between primary and the secondary, if you apply EL, what you get here is N by root 3 EL. What happens to the current? So, if there is a current flowing through the line, and let us say that is I. So, we have I. Now, that I is flowing through the phase, which is the same in the star connection. The line current and the phase currents are the same, and this phase current I, which flows through the primary entering the dot, leaves the dot with a value I by N because of the turns ratio. Now, this I by N, when it comes onto the line, gets multiplied by root 3, because the relationship between the line and the phase in the delta is root 3 I by N. So, the current that you will get here is root 3 by N into I. Simple, isn't it? So, this is the relationship between the primary and the secondary side currents, the star delta. Basically, it is the reverse of the delta star what you saw here. The delta star EL is root 3 n EL, and when you apply I, what you get at the output is 1 by n root 3. The flow of power is just reversed, and the phasor diagram is likewise similar in the case of star delta. Then you have the fourth one, which is the star star connection, the star star. The primary is connected in star or Y pattern, and the secondary is also connected in star or Y pattern, and that is called a star star connection or a Y Y connection. You will see both these names in the literature. In the case of the star star connection, as the name indicates, the primary is connected in star. All the primary coils, that is the AP, BP, CP, are all connected in star fashion, and it is connected to NP, the neutral point on the primary side. And on the secondary side also you have the star format as shown here, and one end of all the secondary coils are connected to the point N as the secondary side neutral point. Now, the A phase is connected to the A line, the B phase point is connected to the B line, and the C phase is connected to the C line on the primary. Likewise, on the secondary side, you have the A, you have the B, and you have the C as shown here. So, you have the A prime, the B prime, and the C prime. So, this is the AS coil, the BS coil, the CS coil. What is important? We have to show the dot polarities. So, we have the dots away from the neutral, dots away from the neutral. Here also the dots indicate that those points of, if the measurement is made with respect to those points, then the phases on the primary and the secondary will be exactly in phase. That is what it means, like as we studied in the context of the single phase transformers. We have of course induction between the primary side and the secondary side, and with 1:n. This is the primary and this is the secondary set. Now, if we apply a voltage EL, what voltage? A voltage EL, effective value to all the phases, all the three phases of the line, and EL will get reflected as a phase voltage of EL by 3. Let me take just one phase voltage, that is the A phase voltage, and that would be EL by root 3, because the phase voltage and the line voltages are related as phase voltage is equal to line voltage by root 3, and this gets inducted or induced into the secondary A phase coil, and that is by turns ratio value n EL by root 3. Now, that is the phase voltage with respect to the neutral n EL by root 3. Now, the line voltage is root 3 times the phase voltage, and that is equal to n EL. Clear? So, you have EL being applied on the primary side, and on the secondary side you get NEL at the terminals of a star-star connected circuit. Likewise, if I pass a current of I in the primary line, I is the same current which flows through the primary phase into the dot, and therefore, the current that comes out of the dot on the secondary is just only I by N scaled by N turns ratio, and that is the line current also for the secondary side. And therefore, if you give I on the primary line, you land up with I by N on the secondary side. So, that would be the relationship between the primary and the secondary. Now, what about the phasor relationships? So, the phasor diagram for the star-star is like this. Let us first copy, go to the next page, let me paste that. So, let us take this up like this, and let me start, let us say, with the secondary side. Now, we know that this is the phase EAS, ECS, EBS. This is the phase voltages, the coil voltages, and that is NEL by root 3 with respect to the neutral. Then the terminal line voltages are going to lead by 30 degrees, and this is NEL. This is also going to be NEL, and this NEL, leading by 30 degrees, the star. Now, the phase voltages of this side of the star, that is the primary side of the star, will be in phase with these, and that will be, let us say, n time, that is EL by root 3. This is the primary phase voltages for one phase, likewise for the other two phases also. And the line voltage is going to lead the phase voltage by 30 degrees. So, therefore, you will have the line voltage EL applied here. This is EAB. This is EA dash B dash. Okay. This is EAP across the primary phase voltage. This is EAS. So, this is how the phasor diagram is going to be related with respect to the primary. So, we see that The line voltage here will be in phase with the line voltage. Phase voltage here will be in phase with the phase voltage there. So let us summarize the four main topologies. So let us say we have the four main topologies, and that is delta, delta, you have the delta, star, and third the star, delta, fourth star, star. So these are the four main topologies. So let us give the relations, summarize the relationship for the currents and the voltages on the primary and the secondary side. So let us draw these columns in this fashion to indicate that we are going to write down the relationship. One is the voltage relationships, voltage, or shall we say line voltage, line currents. The loads are well balanced. The three phase sources are the same amplitude and equally displaced 120 degrees apart, and under these conditions, and at least here we have not considered the practical non-idealities, but as far as the concept is concerned, it is valid still, these following relationship. Now in the case of the delta delta, if we apply a line voltage EL on the primary side, it gets reflected as NEL on the secondary side. And if there is a current, line current I on the primary side, that becomes I by root 3 on the phase coils of each of the primary phase coils, becomes I by root 3 by N in each of the phase coils of the secondary, and it becomes I by N, that is the secondary side line current, where you have a ratio of 1:n as the turns ratio. N is the turns ratio. We will write down N is equal to turns ratio. Secondary voltage by primary voltage, the secondary number of turns by the primary number of turns, which is secondary number of turns by primary number of turns of each coil, for each coil. Then the case the delta star, we apply a voltage EL. It is the same as the phase voltage in the case of the primary side coil. The secondary side coil, it becomes N times EL, and this N times EL is the phase voltage of the secondary side star connected circuit, and therefore the line voltage at the terminals of the secondary side transformer is root 3 N EL. So root 3 into N into EL, and if we apply a line current I, it becomes I by root 3 as the phase current in the primary side, it becomes I by root 3 by n, the current that is induced on the secondary side, and that itself is the line current on the star side, which is I by root 3 into n. Then the star delta, if you apply EL as the line voltage on the primary side, the phase circuits get a voltage of EL by root 3, which becomes n times EL by root 3 on the secondary phase coils, and that itself is the line voltage n EL by root 3, and a current I remains as I in the primary phase coils, becomes I by n in the secondary delta phase coils, and I by n into root 3, I by n into root 3 will be the secondary side line current. And the star star, if you are applying EL on the primary side, it gets converted to EL by root 3 on the phase coils, becomes EL by root 3 into n on the secondary side phase coils, and at the line it becomes n times EL. And if you have a current I through the primary, the current I remains as I in the primary phase coil, becomes I by n in the secondary phase coil, and remains as I by n in the line, because the phase current and the line current are the same in the star connected topology. So, these are the various relationship between the different types of voltages. So, if n is a step up, that is, if the secondary number of turns is more than the primary number of turns, then it is a step up transformer. In the case of a step up transformer, you see that in the case of delta star connection, the line voltage is much higher than what would be the phase voltage by a factor root 3. So, the root 3 is the line voltage is actually root 3 times the phase voltage, and therefore, the coil differential coil voltages is going to be a factor less by root 3, because the line voltage on the secondary star connected is going to be root 3 higher. So, therefore, in the case of the delta star, the insulation breakdown specification is 1 by root 3 lesser than in the case of the delta for the same primary secondary voltages, because here the secondary phase coil and the primary phase coil are seeing a difference of n times EL, whereas here for the same secondary voltage, the primary and the secondary phase coils are seeing n by root 3 as the voltage difference between the phase coils, and therefore, the insulation requirement is less stringent in the case of the delta star. For very high voltage transformers, delta star could be a nice alternative. Likewise, you could study that, you could see that if it is n is greater than 1, the line currents in the case of the delta is going to be less on the secondary side. The phase current in the case of the delta star is going to be I by root 3 n, but on the primary side the phase coils will be rated at I by root 3 rather than I, and therefore, the primary side phase coils can have lesser smaller gauge. So, one could specifically argue along these lines and suitably rate and pick the proper topology of the transformer for a particular application. We stop here and continue in the next class.